Now that we've learned our solubility rules, we can now predict whether a precipitation reaction will occur when you mix two solutions that contain ions. Okay, you can get a precipitation reaction if it's possible for the ions that are in the solutions that you're mixing to combine to form an insoluble compound, a compound that would happen to be insoluble in water. So that compound becomes your precipitate. Okay, so this insoluble compound that you can make, if it's possible, would be what you would call your precipitate. It's going to come out of solution as a solid and eventually settle to the bottom of your container, your test tube, if you mix them in a test tube. So let's see what happens here when we mix lead nitrate and potassium iodide. If you did this, you're going to get a very nice looking yellow precipitate, and let's see what that precipitate is going to be based on our solubility rules. Well, what do you know this lead nitrate is made of? It's made up of lead ions and nitrate ions, right? The 2 here simply means you have 2 nitrates for every lead ion. Potassium iodide is made up of potassium ions and iodide ions. So if you mix these 2 solutions, okay, it's possible to form an ionic compound that happens to be insoluble in water, and you know that that's going to be based on your solubility rule. Okay, rule number 2, if you recall, most iodides are soluble unless it's in combination with silver, lead, and mercury 1 and copper 1. So here's a case where it can combine with lead ions to give you an insoluble compound. So your precipitate, you would expect to have a formula of PbI2. Okay, Pb is +2, iodide is -1, so your precipitate would be PbI2. So your molecular equation for this, your chemical equation would look something like this. Lead nitrate, aqueous, plus potassium iodide, aqueous, yields a precipitate of PbI2. And we label that with an S to indicate that that's not going to be an aqueous solution. Now it's going to come out of solution as a solid. It's called your precipitate. And the other product, well, the remaining ions in solution would be potassium and nitrate, so you get potassium nitrate, KNO3. Potassium's +1, nitrate's -1, so a formula unit of potassium nitrate would just have 1 of each ion. And as a final step, what you need to do to represent this reaction is to balance it. Make sure it's balanced. So let's check. You have 1 lead on each side. Okay, you have 2 nitrogens on the left. You only have 1 on the right, so that means you need to put a 2 there. So, and then potassium, you have 2 potassiums on the right, so you need to put a 2 here. So you also have 2 potassiums on the left. Okay. And your iodine, you have 2 iodines here, 2 times 1, you have 2 iodines here, so that's balanced. Everything should be balanced. Okay, so this is what you would call your molecular equation for the precipitation of PbI2, lead iodide, when you mix lead nitrate and potassium iodide. Okay, so So to complete this, I forgot, I need to put an AQ here to indicate that your potassium nitrate is in aqueous solution. Now, if you look at this, you'll notice that you're dealing with ionic compounds in aqueous solution, and they really are not together in aqueous solution. You know these ions are going to be evenly dispersed throughout your solution, so there has to be a better way of representing this reaction. Okay, and we've encountered something similar to that earlier. We need to write. It's bad. There's nothing wrong with this chemical equation. We call this your molecular equation, but you're writing it as though everything's made up of molecules. A better way of writing the chemical equation for this reaction is to write ionic equation. So in an ionic equation, just to remind you, okay, you only show complete formulas of compounds. Chemical equation that shows only complete formulas of compounds involved in a reaction is called a molecular equation. In an ionic equation, which is a better representation of the reaction when ions are involved, you write formulas of strong electrolytes in aqueous solution as separate ions. Okay, so sometimes when you do that, you might find that some ions are not actually involved in the reaction, and so what you need to do in those cases is omit those ions. Those are referred to as spectator ions. So let's illustrate that using this reaction with lead nitrate and potassium iodide. Okay, so I have it right here. Let's write the ionic equation and the net ionic equation given this molecular equation that we established earlier. Okay? So you'd say lead nitrate, that's a strong electrolyte in aqueous solution, so I have to split that up. I have to write that as lead ions plus 2 nitrate ions. Note, I don't write it as NO3 I don't have I don't have pairs of nitrate ions in aqueous solution. Okay, so I have to write the 2 as a coefficient this time. Potassium iodide, you have 2 potassiums here plus 2 iodides. So I have to separate the iodides, and since I have a coefficient of 2 for Ki, I have to carry that coefficient over to both parts of your Ki. Alright, so what I've done here is broken up my strong electrolytes in aqueous solution into separate ions. And then that gives me, on my right side, PbI2, this is a solid, so I write it as is. You only split up the formula into the formulas of ions when you're dealing with strong electrolytes in aqueous solution. Now, this potassium nitrate right here is made up of potassium ions and nitrate ions, so those should be separated, potassium and nitrate ions. And since I have a coefficient of 2 here, that applies to both the potassium and the nitrates, so 2K plus and 2 nitrates. So what I have right here is what is known as your full ionic equation, or just your ionic equation. It's called the full ionic equation because you'll notice you can simplify it. You'll notice that your 2 nitrates on the left, you have 2 nitrates on the left, you also have 2 nitrates on the right. So what really happened there? Nothing. Nothing really happened to the nitrates. They were just there to begin with. At the end, they're still there. So they did not really take part in the reaction. So you say nitrate is a spectator ion. And just there to watch. Same thing with potassium ions. So you see 2 potassium ions on the left. And you also have 2 potassiums on the right of this ionic equation. So you say your potassium ion is also a spectator ion. So you need to get rid of those spectator ions to come up with what's called the net ionic equation, the most concise way of representing what actually happened. So what actually happened? Your lead ions here. So when you cancel those, I'll just have, so I'm going to do this. Okay. So when I cancel those spectator ions, I will have lead ions plus 2 iodide gives you PbI2. So the only thing that happened here is your lead ions from one of the solutions, from the lead nitrate solution, got together with iodide ions from the other solution to give you a precipitate of PbI2 when you mix those 2 solutions together. This is what you would call your net ionic equation. The most concise way of representing what happened in this reaction.